And there's more coming. There's the usual crew. Good to see everybody. It seems like Governor Cooper is going to be announcing something today at 4 o'clock. And so you may want to choose. I just said 4 o'clock. I could have said any number. I don't know what time it is. I think it's 4 o'clock. But he should be announcing something, and it may pertain to schools and whether or not we'll even be allowed to be enrolled in the fall. And so just be aware that that's coming today. And so there might be a lot more insight into what's going to happen in the next few weeks here. So be aware of that. Let's get started. The first thing I want to do is draw your attention to the As You Learn page. We'll talk about this. Oh, God, today's going to be so much fun. We finally get to leave chemical reactivity. But let me first start by saying, here's the As You Learn page. I'm sure you all are familiar with this. And as we scroll down to unit number 4, so the title, Carboxylic Acid Derivatives and Spectroscopy. We have finished up our discussion on chemical reactivity. Oh, let me scoot. Oh, there's the beauty. On chemical reactivity. And so that is going to be concluded by discussing things like carboxylic acid derivatives, acid chlorides and hydrides, esters, amides, and nitriles. And I have provided links to each of these videos for you to view. They're from last spring, but they certainly are palatable and function very well. Actually, I'm more pleased with those videos than other ones from the spring. So you can reference that material right here. And we will discuss a little bit of this material tomorrow or the next day. I'll summarize it, but I want to give everyone a chance to look this over first. It gives me there's no point for me to discuss this material right here until you all have gotten a chance to look at it. So please take a look at that either Wednesday or Thursday. We'll take a more in-depth look with just maybe even 30 minutes about the major points from these sections. With that being said, and this is why I do this, I backload the class because the more demanding portion of this class is the reactivity portion. And now when you're absolutely gassed at the end of the summer and you're probably couch surfing and you're not living in your own apartment and then you won't be able to for a week, let's move on to something completely different, shift gears, and actually take a look at some really fun stuff, and that is spectroscopy. And you have been inundated with spectroscopy as components of your laboratory, but we're going to really take a long, deep dive into spectroscopy with the one simple question: how do organic chemists know everything that we told you? Don't forget, we're dealing with molecules, and it's not like you can just pick up a molecule and look at it with your hand and know exactly what that damn thing is. That's not a thing. And so if that's the case, of all the stuff that I just wasted our time, not at all, but of all the things that I've done with respect to these reactions, I have left out the most major question. And it should not be satiating to you, this course at this point, because you should be asking the fundamental question of, how does he even know what he's told us? If a reaction has Markovnikov addition, how do they know that Markovnikov addition occurred? What type of instrumentation, what type of techniques did they have to identify the molecule that they made? And we are going to be giving you the skills that you need in order to take a look at those things. And this is my favorite stuff to teach. When I taught at the College of Worcester prior to being here at App, we actually started OChem 1 with spectroscopy. We were the first university to ever do that. And the reason is we wanted to show you the techniques first that led to all the stuff that we know now. And I've kind of flipped that completely in the summer by finishing the course with that. But that's how important this material is, and it is a significant departure from what we've done before. And for those students that maybe the memorization of all the reactions and stuff like that isn't really your cup of tea, that's okay. because this section is really different, and I oftentimes see people doing very well on this section of the course because it is such a change, and a lot of people like the puzzle aspect of this. A lot of people like this approach to answering how do we know what we know. And so that's what's going to encompass our conversation heading into today, tomorrow, Friday, and then we get an examination. And on Sunday, that examination number 4, and I'll talk about this again, will cover all of this material here, as well as anything up to August 2nd. And I'll talk about how the material that I'm covering in the next few days will show up on an examination. But that examination 4 will be an exam, but it'll consist of all of this material. At that point, then you will also be getting examination number 5, which is a take-home, and it's called a composite problem. And basically the idea is you will be using infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance to deduce the structure of a compound for examination number 5. And that shouldn't make any sense to you right now, and that's good. We'll get to that point, but be aware that that's what take-home number 5 is. And then look, we've got Monday of next week, and then final examination, so you're almost done. This will start to make more sense once we get there, but I wanted to give you the layout of what's occurring with the course, so you have an idea what the finishing line looks like, and it's my job to usher us through that. So that's where we are, and again, this is some of my favorite stuff. We are going to start. Well, let me just start by kind of giving some bigger notes, which are. Let's start with the question. How do we know what we know? And then I'll just put in parentheses because that's a really broad thing. Molecular structure. And well, that didn't help at all, so you can't see that. We'll be toggling back and forth between these windows, and so that's what I wrote right there. And in order to determine what we know, this is ultimately a question about molecular structure. How do we determine what a molecule structure is? And I just love this stuff. There are 4 things that we will be using. We won't dive into X-ray crystallography, but we will look at infrared spectroscopy, commonly referred to as IR. We will be looking at mass spectrometry, okay, MS, and there's some variations of this. You could add chromatography in front of this, so maybe you'd see GC, MS, or LC, MS, as different types of things, but this is just some sort of chromatography, which is purification, that precedes the actual measurement of the mass. And this is awesome stuff because I'm going to tell you that as chemists, we have invented a way to measure the weight of one molecule. Just one molecule. And that's going to be the second part of the lecture today. And that should really surprise you because, if you go to the deli at Publix and you order a pound of pastrami, you kind of there becomes a point on the scale where you might get 1.05 pounds or 1.01 pounds, or if you look gorgeous like I do, you always get an extra half pound. But the idea there's some point on that scale where it's just the numbers aren't really significant anymore to the cost. And if you were to look at that, maybe it's a cent, maybe it's 2 cents, but certainly they're not paying attention to the 1/1,000,000th of a cent of weight, and we're going to be able to actually measure the molecule itself and its mass. And then the other one that we'll start talking about tomorrow is nuclear magnetic resonance. And that is some powerful, powerful stuff. And you've already been introduced to this stuff, but we're going to be going back into what is the instrumentation, how does the instrumentation work, how does it produce the chromatogram or spectrum that you're looking at, and then moving forward from that, how do you actually analyze that spectrum to move forward. And so these are the techniques, and I'll just write here. We'll be looking at 13C NMR, and we'll also be looking at proton NMR. And this technique is really cool, and you may be thinking nuclear magnetic resonance, and if you're going to be a doctor, it's the same thing as magnetic resonance imaging. And so really important stuff here as well. I just love teaching this stuff. Now, before we actually go any further too, the idea that I want to stress here is that these techniques are integral in being able to determine what our molecular structure is and its connectivity. And it's going to be really fun to piece all of these things together and end up with a structure. Before we dive into any one of these techniques specifically, let's just take a look at what this information tells us. Infrared spectroscopy, and because it deals with light, it's called spectroscopy. And so nuclear magnetic resonance spectroscopy, infrared spectroscopy. But if it doesn't deal with light, then it's called spectrometry. And so that's why you see spectroscopy for these two. It's implied here. And spectrometry for this one. The nomenclature matters. Spectroscopy infers that there is some wavelength of light. And that definition of light extends beyond visible light and can include any sort of radio waves or anything. Infrared spectroscopy is going to tell us the functional groups present in the molecule. What arrangement of non-carbon hydrogen-based bonds are present? So what I'm suggesting here is the non-carbon hydrogen or carbon-carbon sigma bonds. And some of you may be saying, well, Dr. Shaw, you can kind of see where an sp2 hybridized orbital is. I don't think that's how you guys sound, just so you know. But non-CH or CH bonds, maybe you see an sp2 or sp3 hybridized bond, or maybe you can see a C double bond C bond in an infrared spectrum, and you can. But what I'm saying is really what holistically you're getting from IR is the functional groups of your heteroatoms, oxygens, nitrogens, sulfurs, halogens, those types of things. When we look at the information that mass spectrometry provides, you're looking at the charge to mass ratio, which is the same thing as saying for us the molecular weight of the molecule, the formula weight. And that's not always true. Once you get into larger macromolecules like DNA, proteins, and peptides, those types of things, the charge to mass ratio that we determine from mass spectrometry is not the same as its molecular weight. But for this class, you can assume that the charge to mass ratio that we determine from mass spectrometry is the same as your molecular weight. Then what does nuclear magnetic resonance afford us? Nuclear magnetic resonance affords us the connectivity of the molecule. Okay? And so we're going to just be diving into each one of these things and being able to piece them together to determine a molecule structure. And where we're going to start is with infrared spectroscopy. And so with that being said, let me first pull up this right here. So what is infrared spectroscopy? Let's take a look. First of all, here is a picture of the essentially all wavelengths of or radio or any sort of wave. And of which we have the visible spectrum, which we can see. What we will be utilizing for these measurements of a molecule is the infrared light right in here. So wavelengths that appear right after the red region of our visible spectrum all the way up to the microwave region. Okay, and this right here, you're thinking of energy that's occurring in all of these waves, the infrared region of light. Why are we using the infrared region of light? Well, it's going to turn out that the infrared region of light contains the wavelengths of light that are at the correct energy so that they excite the bonds in the molecule. Okay? And what I mean by that is, let's take a look at how a microwave works. How does a microwave work? Like, here's this question. If you put a paper plate inside of a microwave and turn it on for 10 minutes and pull it out, your paper plate is still cold. But if you were to put and dampen that paper plate with water and then put it in the microwave, you're going to get a steaming hot piece of paper after about 3.5 minutes. Microwaves are tuned to the exact wavelength of light of a water molecule, an OH bond. And when you turn on your microwave, that thing turns on this oscillator that generates that wavelength of light that then impacts that water molecule, and as it impacts that water molecule, it causes the bonds in the water molecule to vibrate and shake back and forth, and that kinetic energy then is translated to the neighboring food, and that increases its temperature. And so if that's occurring with OH water molecule bonds, here's the wavelengths of light that covers the motion of those bonds in organic molecules. We'll also be using these radio waves and NMR down the road. But that's the region of light, IR, the infrared region, and the reason why is because that contains the energy of bonds that are capable, did that make sense? The energy of the wavelengths that are at the appropriate energy to excite the bonds in the molecule. And we'll talk about what the heck is happening there, but that's the region that we're going to look at. Okay, and I love this stuff. Here's a picture of an FTIR, and here's this Nicolette IS5 FTIR spectrometer from Thermo Fisher. This is the one that you have in the organic chemistry laboratory. Let's see if this pulls it out. Certainly a beautiful, beautiful instrument. And keep in mind, I'm going to say this. Please remember this part right here. It won't really show up on an exam, but these things are called instruments. You guys are all scientists now. And so instruments are things that take a reading of a sample. Machines are things that take energy and convert them into work. Work being motion, work being heat, work being something that can be used to impart some type of Newtonian type physics. Since we don't do any work on our system, these things are called instruments. So don't ever make the mistake of calling these things machines. They are not. The IR instrument will not take over the world. Boston Robotics are making machines that absolutely will eventually take over the world. If you've ever seen their robots that have like the flipping dogs that can chase and like completely walk upstairs and land on their 4 feet, yeah, that's the last thing I'm going to see before I die, that's for sure, once those go sentient. But the idea here is don't make that mistake. These are absolutely instrumentation. You're looking at something that looks the size of maybe like a microwave oven, okay? And you can see, of course, they use an Asian person. You can see the size right here. So a really small instrument. And what's on the top of this instrument is actually allows you to take a solid sample, but more typically than not, these infrared spectrometry is done through a salt plate and in a liquid form, but they do have solid options as well. Taking a look at the price, you're looking at about $4,000 for an IR spectrometer, a good one. Here's some smaller ones, but the benchtop ones that you're using typically range in the $4,000 range. And before I go into the details of what the heck a spectrometer is and how it is used, the IR kind, I want to draw your attention to this. Here's a picture of this guy with this spectrometer. And if this guy wanted to keep his job, then that guy would never ever pick up this instrument, turn around 180 degrees and drop that on the ground. That is not something that would fare very well for this instrument. But check this out. This is a picture of the science and the sample analysis at Mars tool called the SAM, which is on the Curiosity rover. Okay, this thing, if you believe that this exists, that thing right there is on the surface of Mars, and inside that thing is a tunable laser spectrometer, which can be tuned to the IR region to analyze molecules that are found on the surface of Mars. And you can only imagine that the journey of that spectrometer was probably taking one of these things, putting it inside a rocket, on a rover inside a rocket, shooting it off of this planet, flying it through space, dropping it onto Mars. It lands on Mars and is still fully freaking functional. And scientists did this and engineers did this, and that's absolutely fascinating. The same instrument that you have in the organic chemistry laboratory is the same instrument that they have on a rover, actually two of them, on a different planet in the solar system, and that is fundamentally fascinating. I would never ever want you to drop that instrument even 1 inch on the bench top, but they've dropped that from thousands of miles away, and it's just absolutely fascinating to me. Let's talk a little bit more about how IR works. Infrared spectroscopy is going to be using the wavelength of light that is really at that region in a molecule where the bonds are. So every bond in a molecule has its own energy. And what type of theory did you learn that can talk to us about the energy that a molecule has, the bond does? You are looking at molecular orbital theory is the only theory that you know that contains information about the energy of a molecule. And as a result, that energy of those bonds in that molecule can all be tuned and excited with this IR light. And so what I'd like to do here is first sketch out the schematic of this and talk about what's happening when we look at what's going on inside an instrument. And so the schematic is such that you have really a light bulb. And I don't know if I can still draw light bulbs like this because people don't see them all that often. But this is your light source, not this old school incandescent type. And that light bulb is going to generate IR light, IR wavelengths of light. Okay, so that's one component that's in that instrument. And then that light travels down a path, and it becomes, it interacts with, typically, your sample. Right here. And then that light then travels through here to a prism. And when you think about what impact, and I'll show you this, what impact does a prism have? Well, a prism has the impact that as a kid you probably saw. If you saw, like as a kid, sunlight hits your prism and all of a sudden you get to see the colors of the rainbow. That same thing is happening here inside your sample. So you've got this prism, and you're also thinking that Dark Side of the Moon, Pink Floyd Dark Side of the Moon cover, if you know your album covers from Times Are Changing, Sadness. But you have a prism, the light's going to show up. And then what you have is some type of slit, then a detector, and then your CPU. And at the end of this, you end up with some sort of a spectrum. And I am going to redraw this because just splitting two things here. I believe I have this backwards because the slit should appear before the prism, I believe, because that would absolutely make a lot more sense moving forward. So we'll just swap those two things, because you will see why in just a second. So we'll put this slit right here. This makes a little more sense. And then we'll put this prism here. Oh, this is so fun. Okay, so let's envision we're going to have to use the visible spectrum of light to kind of represent the different wavelengths of light that could be generated with this IR light. But understand, unless you're like a gecko or something, that I don't even know biologically if they can see the IR light, but if we can't visually see the IR spectrum of light. But the idea that I'm going to use is that this IR wavelength of light, or this light source rather, is going to generate a few different wavelengths of light. And how I'm going to capture this is with different types of colors of light to suggest that each and every single one of these wavelengths is, in fact, a different energy. And the way that we associate that is with color in our visible region, so I'll continue to use that right here. You turn on this instrument and boom, light turns on just like a light switch. Boom, on, turns it off right away. And so all of a sudden, all these different colors of light are turned on and they interact with your sample. And so let's take a look at what's happening with each and every single one of these colors. So let's say that the red does, it's going to be a long day. Does, D-O-N-D-O-E-S. Red does not possess, let me rewrite that, is not at the correct energy. Does not possess the correct wavelength to interact. And I haven't told you what the light is doing to the actual molecule. I've alluded that it's kind of making it vibrate a little bit. But what I'm suggesting is that when this light bulb gets turned on, this light hits the sample. There is nothing in the sample that starts to interact with that wavelength of light. And how that happens, I don't know. And so it goes through this sample, and the slit here isn't drawn so that I can show this passing through, but the slit reduces the total amount of light that the detector can exist and see. And so this whole thing passes through the slit, and then the prism starts to deflect it, and it hits this detector, and all of a sudden it's going to show up right here in our spectrum at here, and it's going to show up somewhere on our spectrum. And I'll come back and define the Y and the X axis in just a second. Let's say then that as you turn on this light bulb, the orange wavelength of light comes flying through here, and all of a sudden there is a bond in our molecule that kinda is tuned to the right energy. It's not necessarily the correct, but kinda tuned to it, such that some of that energy is absorbed by the molecule, and some of it passes through. And so the idea is orange possesses the wavelength of energy E-N-E-R-G, where some interacts with the sample. It hits this slit in the prism, and it gets deflected, and it hits our detector, and that's going to appear somewhere else in our spectrum, right here. I know that doesn't look as clear as a dot, but you guys can get through. Look at this. That green wavelength of light hits that sample, and all of that energy is absorbed by the molecule. All of that energy is translated into some molecular motion inside that molecule, and all of a sudden none of the light makes it back through, and that means that it's going to appear somewhere else in the spectrum. Okay, so green wavelength, and again, it's not color, but you get the idea. Different colors are different wavelengths, and so different wavelengths here represented in the IR range by different colors possesses the wavelength of energy that interacts with the sample. I'm going to write completely. Okay. And then what I'll follow through here with the blue is the same idea that happened with the orange, where that is going through the slit, it hits the prism, some of that energy was absorbed by the sample, and then all of a sudden you're going to see that appears somewhere else in our spectrum. So that's what's happening. So we'll say blue over here. That's what's happening inside the instrument when you tell it to take a sample. And so light goes on, boom. Some of the light is absorbed by the molecule. Some of the light is not. Red was not absorbed. Orange, some of it was absorbed. Green, all of it was absorbed. Blue, some of it was absorbed. And what your instrument is doing is it turns it on, takes a reading, does it again, does it again, does it again, and every 4 samples, then if you've done any sort of Fourier transformation, partial differential equations, that is the type of mathematics that you need 4 scans in order to convert that what you end up with is this weird looking squiggly thing that then gets translated into your spectrum in the computer, and that Fourier transformation occurs every 4, and so you tip 4 scans, and typically you'll see 4, 8, 12, 16 different scans used to collect your samples, and multiples of 4. And so that's typically what's observed in this setup. And so what I want to talk about then is what's happening inside that sample. So what we'll do is we're going to take a close look. And why is this stuff even important right now? I would venture to say that this is the most important stuff that I could possibly teach you if you're going off to a career in medicine or anything that involves a professional school, because this is the exact same type of stuff you will be seeing in your professional career. And what do I mean by that? What I mean by that is you are going to be learning of how an instrument takes a reading, how it produces data, and how you interpret that data in order to determine something about that sample. Let's rewind that. In medical school, you will learn about a test. And if you learn about that test, you can then get its results from that test, and then you can use those results to inform you about what you believe to be the ailment for that person. It's collecting data through a set of experiments, understanding what that data means, and then understanding how to use that data to deduce some type of information. And so if you have Crohn's disease like myself, I've got some very competent doctors that have taken data from 20, 30 different tests and probes. It's been horrible. But they have pieced together those data in order to make an educated decision. And I think the most important thing about being able to do this is you have to absolutely understand your tests. You have to understand how for instance, COVID-19 test works so that you can understand where the fallible portions of that test are and where the infallible portions of that test are, so you understand the 90% accuracy or 95% accuracy. If you understand how the test works, you can understand your confidence in the results that you get. And so as you head off to medical school, I implore you to always understand the test that you are getting data from, to understand when or when not those tests need to be trusted. And so looking at this, let's take a look at the actual physical interactions that are occurring between this light and our sample so that we can better understand why the spectrum looks the way that it does. When we look at the interactions that occur in this sample, and so we were looking at the idea of the red wavelength of light going straight through the sample. Then we had the orange wavelength of light where some of the light, all the light hits the sample and some of it is used to make that molecule move. Then we talked about the green wavelength of light where all of that energy was absorbed by the molecule. And then we talked about the blue wavelength of light that looked a lot like the orange wavelength of light. So what's happening in there? Well, if we were to say the sample right here was a molecule of ethanol, which I'm going to have to completely draw in its Lewis structure, what I'm suggesting is that this light can interact with this compound and get different types of results depending upon whether or not this molecule is susceptible to interacting with that wavelength of light. So how do molecules interact with light? If you were to look at a very classical and simple definition of a bond, you would be looking at the idea of having two atoms that are separated by a spring. And the idea is that when a wavelength of light hits that, why am I using a partial equation here? Just use the sign. When that wavelength of light hits this molecule, it could cause this bond to vibrate. And that means that this atom up here will move away from the other atom. And just a simple bond, that, let me position myself. This type of bond stretching is what's observed here. And the idea is here's atom 1, here's atom 2, and when that wavelength of light hits this bond right here where my face is, once that happens at the right energy, if that wavelength of light has the right energy, it's going to cause these atoms to start to stretch back and forth with respect to one another. This is called a stretch. And just like the idea, and this is always tying together all these other things you've learned in other classes, energy is conserved, and so if the wavelength of light is dialed in perfectly to this right here, it'll cause those bonds to stretch, and maybe if it's not quite, maybe if instead of light blue, it's like dark navy blue, then maybe it's not quite the right energy, but maybe you just get a little bit of stretching. And the idea is that energy is either proportionally and quantifiably translated into some type of molecular motion, of which a stretch is one idea, then if it's the right energy, you will see some of those interactions taking place and that molecular motion occurring. Well, if that's the case, then when we start to look at this molecule, well, then let's take a look at a slightly more developed way of looking at the interactions and bonds in a molecule. So we'd be saying atom number 1, atom number 2, and atom number 3. What are the ways then when these energies hit these molecules, how can they make the molecule or the bond start to move? It turns out, and I'm going to use my head as an atom right here, and then these hands as the other two molecules. What I'm suggesting here is that when this wavelength of light hits this molecule, perhaps these atoms 1, 2, and 3, they move. Both of them move away from one, so like these two are moving away from that center molecule, and so they're going up and away when that happens, both moving in the same direction. This would be called like a symmetrical stretch. You could envision one moving closer to the atom number 2 and one moving away. This would be called an asymmetrical stretch. There's things that can occur, like maybe like the atoms, instead of stretching outward, they kind of go whoop upward and spring away like this. And so the idea would be that like atom 1 goes up this way and atom 2 goes up this way. What are those things called? I can't remember. I'll fill that name in once I look it up. It's just escaping me right now. Bend. So this would be a symmetrical bend. That's where I'm at. The word bend is escaping me right now. But here's the asymmetrical bend. And then there's also the option to like have this sucker twist and this sucker twist like this. So like really like a corkscrew type twisting. And those types of motions can be, you've got like an asymmetrical and symmetrical twist. And so just what I'm really trying to suggest is there's a lot of different ways that atoms within a molecule can start to move with respect to one another, provided that the molecule or the wavelength of light is at the correct energy to make that motion occur. And I've done kind of a disservice here because I've suggested that this one wavelength could make any of this happen, but what I would really want you to understand is that maybe this is like wavelength 100 nanometers, and this is like, and that's not even remotely close to the right wavelength. But I just want to show you like the energy that's required to get a symmetrical stretch would be different than the energy required to get a asymmetrical stretch, which would be different than the wavelength of a bend, a symmetrical bend, which would be different than the wavelength of a asymmetrical bend. And maybe you're looking at a wavelength over here of different wavelengths. And so the idea being that if every bond is different, it will require a different wavelength of light to make the molecule, scratch that, bonds move. Substatement, different motions require different wavelengths of light as well. So kind of the idea that this bond right here, this carbon-hydrogen bond, has its own wavelength of light that will excite it, and then in that subcategory of wavelength of light, if you want to think about it like that, the motion of this carbon-hydrogen moving this way with respect to this carbon-hydrogen moving this way downward is going to have a slightly different energy than both of these hydrogens moving up with respect to that carbon and down with respect to that carbon. Just molecular motion, the bonds in that molecule, are all at different energies, and they're all going to require different wavelengths of light. Oh, I love this stuff. So when it hits, then it goes through the prism, and it gets deflected, and then it goes through the slit, and again, I think I flipped those backwards, and then it hits the detector. Computer does the Fourier transformation, and then all of a sudden, at the end of that Fourier transformation, you're left with this beautiful spectrum that places 1 over the wavelength, which is also called the wave number, on the x-axis, and then on the y-axis, you are likely to see absorbance. And so you're thinking here, why is it a wave number? Well, wave number allows us to go from anywhere from 4,000 down to like 800 inverse centimeters is the units on that. And why do we use inverse centimeters? Because if you use regular centimeters, then those wavelengths of light would be like 1.08 times 10 to the like 8th wavelength of light, and that's a lot harder to talk about than just like 4,000, 3,400. And so all we've done is just placed the wavelength of light in the denominator so that the numbers become easier to speak about. And then the absorbance is just how much of that energy was absorbed by the molecule and translated into some sort of molecular motion. And when we look at this, you have 100%, and then you have 0% absorbance. Or another way to look at this would be percent transmittance as well. But more importantly, the idea, regardless of which one of these you're using, is that red wavelength of light, it passed straight through our sample. It did not at all interact with our sample. And so at that point in time, at that wavelength of light, we would expect 0% of that energy to be absorbed by the molecule. Some of that energy was absorbed by the orange wavelength of light. All of that energy was absorbed by the green wavelength of light, and some of that energy was absorbed by the blue wavelength of light. And what you end up with is a spectrum that places the energy with respect to how much of that energy was absorbed by the sample. And what you end up getting out of this is, woohoo, not that at all. That's a mass spectrum. Let's move to the other one, the infrared spectrum. Here's the infrared spectrum of ethanol. And so what I'm suggesting here when we look at this infrared spectrum of ethanol is that here is the wavelength of light, 3,000, and at 3,000 in your wavelength of light, there was something in that molecule that absolutely started to flip the heck out and start vibrating incredibly fast when it encountered that wavelength of light. And it just so happens that is a carbon-hydrogen stretch. This 3,400 out here, it turns out that the oxygen-hydrogen bond gets insanely excited by a 3,400 wavelength of light, and it starts to go apeshit and starts to vibrate back and forth incredibly fast when it gets encountered with that wavelength of light. Out here at 1,800-ish, 1,600-ish, I guess, 1,400-ish, at that point in time, there is a bond that is partially excited by that wavelength of light. And when it's partially excited by that wavelength of light, some of that light is translated into molecular motion, while other aspects of that light are not translated into molecular motion. It passes through the sample. Maybe 40% of it does. I think, well, not even maybe. We're looking at 30% of that sample is not absorbed by the molecule. It passes through that sample, goes through the slit, hits the prism, gets deflected, hits the detector, and then shows up at that position in our spectrum after Fourier transformation. At that point in time, every single type of bond, that should be the take-home message, every single type of bond in our sample has its own energy, and when it comes in contact with that energy, it starts to become excited. And so perhaps, and I'm not necessarily saying that this is true, but when we look at the sample of ethanol, this red, it passed through the sample and there was nothing that got excited at all. And so maybe we're looking at the 3,900 inverse centimeters in this spectrum of ethanol. So we'd be looking at this right here. I'm going to try and do some double time. I wrote 3,900 right here. And maybe this orange sample then, some of that light hits this right here, and all of a sudden it causes this hydrogen to move way up here and this carbon to move way down here. And some of that energy absorbed and some of it's not. And so maybe some of that energy gets absorbed by the sample and you end up with here at maybe 3,600 inverse centimeters, where some of that energy was tuned perfectly for that bond, and it started to make those atoms in that bond start to wiggle and move. Maybe we're looking then at this green section, and all of a sudden that green section comes flying through here, and we end up getting massive response by this molecule. And this carbon and this hydrogens, maybe this is causing it to corkscrew this way, and this energy causes this portion to corkscrew this way, and we end up with a point where we see an immense amount of absorbance. So maybe we'll say 2,900 inverse centimeters right here. All of that energy was absorbed by the sample and caused those atoms to twist with respect to one another. And then the blue portion again here is the interaction perhaps and passing through that maybe made this and this portion move in the same direction with respect to one another, and you end up with the sample that's maybe at, let's say, 2,800 inverse centimeters. What I'm just trying to say is every bond has its own energy. Every bond then has its own motion that's codependent on a slightly different type of energy, and those energies are being afforded by this sample, by this light source that's tuned to the infrared region. Now, so if that's how the sample is taken, how the instrument works, and again, don't forget, this sucker, there's one of these instruments on the surface of Mars working right now. Hey, that's pretty cool. Let's take a look then at this. What the heck is this thing? Well, if you look on As You Learn, let me pull up the website. You will find that on As You Learn, there is a thing called a spectroscopy data sheet, which is this thing right here. And if you click on that, it should produce this document right here, which is something that one of my colleagues at the College of Worcester made. You can see back in 2009. But what this is a representation of the different types of bonds that could be found in molecules and where those bonds are tuned to absorb wavelengths of light at a certain wavelength. And so when we look at, let's say, the 3,500 inverse centimeters region on an IR spectrum and ask ourselves, what the heck, if we see a peak at this point, could that be a result of? Then perhaps when we look at this table, we would see, well, there's nothing at 3,500, but let's say 3,300 inverse centimeters. We would typically find an OH at that 3,400 inverse centimeters. It turns out that a C double bond O carbonyl is perfectly tuned to absorb the wavelength of light that is found in an aldehyde or ketone or carboxylic acid at this 1710 inverse centimeters that occur. And that is a really powerful thing, that this molecule will absorb that wavelength of light. You can use this table all you want on any examination that we have for the remainder of this class. When we start to look at an IR spectrum of something like ethanol and ask ourselves, mass spectrum, sorry everybody, let's go to the IR spectrum. When we look at this molecule and ask ourselves, well, here's the spectrum of ethanol, and here's a peak that I observe at 2,900 inverse centimeters on our IR spectrum. Well, if that's the case, then, I wonder what that could be. And so I go over to the spectroscopy data sheet and say to myself, oh, at 2,900 inverse centimeters, just below 30,000, any sp3 hybrid carbon-hydrogen bond will start to do some type of molecular motion at that point in time at that wavelength of light. Ergo, I must, if I see a peak at 2,900, have this type of bond, a CH sp3 hybridized CH. I've got a peak out here at 31, 2, 3, 33, 3,300, 3,350-ish. 3,350-ish. Hey, I wonder if I have an OH present in that molecule. And so every single one of these peaks can be correlated back into some specific bond. There becomes a point that occurs in our spectrum where things get insanely busy. And that's this region that's highlighted by something called the fingerprint region, which exists between 600 and 1,400 inverse centimeters. At that point in time, we are getting to the energies of bonds and molecular motion that are all very much tuned specifically to the molecule. Ergo, that region of the molecule, from here up to about here, consists of peaks that are solely unique to that molecule and can be identified through this region. But what that also means is a lot of peaks are going to show up in this region. And as a result, this region here is not very good at being diagnostic for what could occur in that molecule. If you look over here, I don't have any association to a certain type of bond in this entire region because, look, there's tons and tons of peaks that occur here. It's going to be really hard at your level, and even my level, for instance, to determine exactly what type of molecular motion is occurring in the molecule at these wavelengths of light because there's just so many of them here. This is a non-diagnostic region of this portion. The same idea would be like if you took a CAT scan of a brain, let's say, and at that point in time when you took that CAT scan, you also got the scan of the ears because they're attached to the head at that point. You wouldn't be looking at the ears for a diagnostic confirmation of a brain tumor because it's just not the area of the scan that's going to be diagnostic in determining a brain cancer. And so you wouldn't look at that portion. You're not going to look at this portion to be diagnostic for anything because it's just too busy. There are other regions of this molecule where certain arrangements of atoms definitely appear in between the 16 to 1800 region, right in here at this 2300 region, right out here at this 2800-ish to 3500-ish region of the molecule. But there are also some dead zones where in most organic molecules you won't see any absorbencies because there's no bonds that are tuned to that energy. What I want to do right now, because I have the worst dry mouth on the face of this earth, I need to get some water. Let's take a 10-minute break, and then we're going to come back and look at some more specifics of IR, and then we'll head into mass spectrometry. So we'll take a quick break.